Alright, so we have this first order um, first order inductor circuit. Alright, we need to find this here, what the current as a function of time through the inductor is. Right? So what we're going to first do is solve for it before 0. That is our first step. And here's the circuit. Before 0, that switch here is closed. Because at t equals 0, it switches open. So before that happens, this is what it looks like. You have this shorted here, and the current passes through the short, avoiding that power source. So this power source is eliminated entirely from the circuit because it is shorted out. And if you're wondering what actually is going on here, what's this power source doing? Well, its voltage is just going whoop through this loop and back to itself. It's staying constantly in here, not affecting anything. It's like trapped in a box kind of deal. And then if you want to look at this voltage source and kind of maybe understand it a little, it's traveling this way, and through these two paths to ground and back to here. Kind of ordeal. Hopefully that might, clarify kind of the path of its current slash voltage is kind of taking voltage is pressure, current is, how the electrons move. Anyways, we need to figure out the initial current across that inductor there. So in order to do that, we know that as this circuit, for t before 0, the inductor has sat for a very long time. And inductors that sit for a very long time are shorted. They are a short circuit. That is what they act like. So it's shorted. So we need to find the initial current through this shorted wire over here. Okay, so since we know that this voltage source is irrelevant, let's erase that. And let's redraw this circuit so that it looks more digestible. That looks better. Okay, so we have this happening here. And wait a minute, what happens with this 6 ohm resistor here? Well, after the current passes through this one resistor, it says, which path is easier? We're going to take the shorted path. That 6 ohm resistor becomes irrelevant. So 50 divided by 2 for voltage is equal to R times I. 50 divided by 2 is 25 amps. 50 divided by 2, 25 amps. That's the path it's taking, around and around, like so. Okay. So that wasn't too bad. Nice and simple. Okay. So we start off with 25 amps. 25 is equal to I naught. Now let's solve for t after 0. I didn't draw that, so let me draw that really quick. Okay, so this is t after 0. Now that power source is no longer shorted. It's introduced back in, right? So what do? It kind of might look a little weird, but you see how they're the same polarity, minus to plus, minus to plus? Well, the thing you can do with voltage sources is you can add them together. Well, that will become 100 volts. And that you can only do that because they're right next to each other, like so. Okay, well, what is the final current through this circuit? Well, let's see. This is our final state for the time after 0. Let's say for funsies, since it goes to infinity, this will become shorted. It's a shorted wire. Okay, we have the same scenario. Goes through this resistor from the power source. It goes to this point. Easy path this way. There's no resistance this way. It's going to take that path. So the 6 ohm resistor is once again ignored. It will play a part for when we find the dampening factor. I'll explain that in a second. Don't worry about that. Okay, so it's 100 divided by 2. So we get 50 amps. That will be our final value that it approaches. I infinity, right? Okay, so now what we have done is we found what we start at and what we finish at. That is the most important part for all first and second order circuits. We need to know what we start and what the final value is for both. And then we can figure out after that how is it changing during that time. So the formula for that, this is just something you can remember. You could actually derive it, but it's a little hard. I don't want to really do Laplace transforms or anything like that. So the formula is I final, I'm using I because we're doing current for this one, plus I naught minus I final plus E, not plus, times E to the negative, let me remember this. I always do this to remember what goes up in this exponent up here. Let's say you have an inductor, and let's say you have a resistor, right, like so. We do voltage, right? Let's do a mesh, a KV, Kirchhoff's voltage law. Voltage is equal to R times I, and voltage across an inductor is equal to inductance times di dt. Okay, you divide the L over. All right, let's do it like this. Plus Ri, divide the L over. We don't want anything with the highest order of the equation. You get R over L, right? And then if you remember differential equations, it's going to be M plus R over L. Subtract the R over L to solve for M. Negative R over L. Oh, we found it. Okay, we're good. So we get R over L. And if you saw I wrote negative R over L over here, why didn't you bring that negative over? I already put it. That's where this negative came from. Okay, so times T. E to the MT. Hopefully you remember that from differential equations. If not, it goes like simple. We'll do a quick example. We do I is equal to E to the MT. And you substitute that in for I into this differential equation, grab the derivative, and you can find what di dt is. Blah, blah, blah. Let's not blabber on too much. Okay, so we got this equation. Now we need to plug everything in. So I final we know is 50 plus I naught. What is I naught? 25. 25 minus 50. E to the what? R over L. Well, what is R? We need to find the equivalent resistance seen by this inductor right now. This inductor is located here as it changed. Oh, there's Patrick. It's Patrick. Okay, it's all right, Patrick. I appreciate it. Gotta love Patrick. Let me put on for 1 hour. Okay, back to this. R over L. Okay. We need to find the equivalent resistance right here. This is where the inductor is. I know I just erased it, but I can put it back. It is shorted as it, goes to infinity, but just for this point, we need to find the equivalent resistance seen by the inductor. That's what this value is. So to find that, we're going to do some Thevenin stuff, right? So we're going to get rid of this inductor, and we need to find the equivalent resistance from point A to B. A to B. So you can short power sources, voltage sources. I call it power sometimes. I don't think that's right. And we see that from point A to B, we have two paths. And the 2 ohm and 6 ohm are in parallel. So we can reduce that by using a calculator that's in my pocket. Let me grab that real quick. So 1 over 2 plus 1 over 6, and grab the reciprocal, we get 1.5. That's a nice number. Negative 1.5 divided by what? What is the inductance? 3? Wow, that works out really perfect. E to the negative 1/2. That's so weird. I've never had a number like that. So we get 25 minus 50. We know what that is. It's negative 25. E to the negative 1/2 t 50 is equal to I as a function of time across the inductor. Nice. And that is the value. And to see if you're right, if you plug in t at 0, we get 50 minus 25, and that's 25. That's the initial value that we start at as it changes over time. And on a graph, we start at, we'll call this 25, and we go up to 50, something like this. I is a function of t. Checkmate. So yeah, that's how it's done.